In this video, we're going to talk specifically about the sampling distribution of the sample mean. We've already taken a look at sampling distributions, and we mentioned the repeated sampling nature and how we go and for each of those samples we're taking, we calculate a value of the statistic and we pile them up. Well, now we're going to be specifically talking about sample mean. So we're going to go to a population, take a sample, calculate a value of the X bar, and think about doing it over and over and over again. There are certain properties, certain things that we need to know about the sampling distribution of the sample mean before we can get to the confidence intervals that we're kind of building towards. So we talked about two ideal properties of sampling distributions. We said that the mean of the sampling distribution is centered at the parameter it's estimating, the unbiased nature. That's one of the properties we talked about. And when we talk about the mean of the sampling distribution of X bar, we'll write it this way. Mu sub X bar is centered at mu. And now the picture that I want to draw that corresponds with this, see if I can draw a decent little picture over here. What we're saying then is that if this is the X bar distribution, now in a little bit we're going to see that we're going to get a normal distribution. We're going to say it's centered at mu. And so the X bar distribution is sometimes bigger. Sometimes the value of X bar is bigger than mu. Sometimes the value of X bar is smaller than mu. But on average, it's centered right where we want it to be, right at mu. The second result is that the standard deviation of the sampling distribution of X bar is sigma divided by the square root of n. And it's this denominator here, the square root of n, that's going to get you. That's going to be a trouble. And students have trouble remembering. It'd be really nice if I could tell you that the standard deviation of the X bars is sigma, so you could say, it's just mu and sigma. Doesn't work that way. Earlier, we looked at an example where we talked about how as our sample sizes increase, and I think I did it in the context of a distribution where we're trying to estimate the age of students. And we talked about how sometimes you get older students in the sample, and they have an impact. If I take a sample of size 2 and I get a 50-year-old student, it has quite an impact on that sample mean. But as my sample size increases, that 50-year-old student, well, if I took a sample of 20 students, a 50-year-old student is going to be balanced by a bunch of 19, 20, 21-year-old students. So while you still have a 50-year-old student in the sample, in fact, you have a better chance of getting a 50-year-old in a bigger sample, the impact of that age is lessened. And so we say that the sample means get closer together as our sample size gets large, and where you'll see that is with this little square root n in the denominator. So these two things, these are two properties of the sampling distribution of the sample mean that are always true. Doesn't matter if you take large samples or small samples. These two results are true. These two properties are true. And by themselves, you can do absolutely nothing with them. We need the shape, and that's where we go next. We're going to say, we get the shape two ways. We're going to say, if the population we're sampling from is normal, it's a big if. We don't usually know the shape of the population, but if we do, if the population we're sampling from is normal, then the sampling distribution of the sample mean is also normal. I had said when we did that age example that for small sample sizes, the shape of the sampling distribution looks like the population that you're sampling from. So if you're sampling from a normal curve, the sampling distribution will be normal as well. The problem we run into is that in a lot of situations, we don't know what the population looks like. And so that's where the second one comes into play. If the shape of the population is not normal, which is going to be most of the time, so I'm going to put a little asterisk here by this one because this is the one we rely on most of the time. We rely on something called the central limit theorem. And the central limit theorem says as long as our n is sufficiently large, the sampling distribution of the sample mean has, we're going to say, an approximate normal distribution. It looks a lot like a normal distribution. An approximate is going to be close enough to normal that we're going to be able to work with the normal distribution. If n is sufficiently large, well, what's a large sample? Interesting question. A large sample depends on what you're doing. As you move further and further in statistics, you're going to find that there are different sample size criteria. There's different ways of defining sufficiently large, depending on what you're doing. Here, when we're working with the sample mean, our sample size criteria is that n is greater than or equal to 30. That's a sufficiently large sample when we're working with the sampling distribution of the sample mean. Now I know as we go further into confidence intervals, which is our next topic, I know that we're going to be working with means and proportions. And while the means have a sample size criteria of 30 or more, the proportions will be something different. So don't get too married to this sample size criteria because it will change. It's going to be 30 or more through the sampling distribution work we talk about, because right now we're just concentrating on the sample mean, but that will change later on. Now I do want to point out something about the central limit theorem. Sometimes people present the central limit theorem and they just say this part here. However, this is why it's such a big deal. This works regardless of the shape of the population that we're sampling from. Doesn't matter what we start with. Let's put a period in there. Doesn't matter what the distribution looks like that we start with. So if the x's look like this, crazy distribution, if that's the x's, well, when we take small sample sizes, the x bars will look kind of like that too. But when we take 30 or more, the x bar distribution, if this thing is centered at mu, I'm going to draw a picture, it's going to be weird here, and then I'll explain it with some examples in a little bit. The x bar distribution, if you go back to these three things we've learned, the mean of the x bars is also going to be mu. The shape is going to be approximately normal, and then the standard deviation of the x bars is going to be sigma over the square root of n, and so we're going to end up with something that looks like this. And actually using my mouse, I didn't do such a bad job. Why is it so tall and skinny? Because the standard deviation of the x bars is a lot less spread out. The standard deviation of the x's is sigma. Standard deviation of the x bars is sigma over the square root of n. And because I'm talking about a large sample to get the normal curve, it's going to be a lot taller and skinnier. The idea is at some point, not too distant future, we're going to try to estimate where the value of mu is, and we're going to just pull one of the values from this sampling distribution out, and we're going to get a pretty accurate estimate of where the value of mu is. All right, so now with these three things, and I think I summarized them on this next page. Oops, not yet. With those three things, we get to do some stuff, and really what we're going to be working with is normal distributions again. And so we've seen this before. When working with normal populations, we created a z-square, x minus mu over sigma. That was what I will call the x version. When you have a normal population of x's, you can create a z-score using the x version. Now we're going to use the x bar version. We subtract off the mean, we divide by the standard deviation, except now we're working with the standard deviation and the mean of the x bars. And so what you see is the new z-score. And then notice these two z-scores. Look at this guy up here, look at this one, and look at this one. And you can see the numerator, subtract off the mean. It's the denominator. It's the sigma over the square root of n in the denominator. That's different. Okay, now I'll summarize. Here are the three things. 1, 2, 3. These three pieces allow us to do some work. If you kind of close your eyes and look away from the screen for a second, if I tell you have a normal distribution and you know the value of the mean, you know the value of the standard deviation, we can do some work with that. We can change it to z-scores. And if you've put in the time, if you've done the work, if you've kept track of what we've done in class, you should already be pretty proficient at working with standard normal distributions. If you can work with standard normal distributions for x's, there's no reason you can't work with them for x bars. A lot of similarities. Big difference in that square root of n, but the way that we're going to solve it, the way we're going to approach it, very, very similar. And so that's the next step. Let's take a look. Let's see how we work with the sampling distribution of x bar. I'm going to do two examples. This first example, I just want to kind of go through this first example to go through the nuts and bolts of the sampling distribution work, to show you how it works, to talk about the pieces that you might be asked about later. And so hopefully with this first example, you'll be able to work with sampling distributions of x bar. You'll understand how to work with them. And then the next question is, well, if we have these two different types of problems, the x problem and the x bar problem that work with normal distributions, how do I know when I'm working with x and how do I know when I'm working with x bar? What are the clues? What are the pointers? What are some things I can look for to differentiate between x problems and x bar problems? So let's start with this. Let's learn the kind of the mechanics, so to speak, of working with the sample mean. And so in this example, I'm setting up a population. Coca-Cola is a pouring machine that dispenses soda into 12-ounce cans. The machine has a distribution with a mean pour amount of 12.05 ounces, and I think we looked at an example like this earlier. The cans actually hold more than 12 ounces, so that's possible. So the mean is 12.05 and the standard deviation is 0.025 ounces. Now suppose 100 sodas, and that's a sample size, that's n, and right away you probably notice, it doesn't look like n, but that's what I'm trying to write here, you probably notice a couple things about this sample size. First, it's bigger than 30, it's large. But there's maybe something, a second thing you notice, and sample sizes that I'm a pretty big fan of are sample sizes like 36, it's bigger than 30, 49, 64, 81, and then 100 is probably my favorite sample size. What do those numbers have in common? 36, 49, 64, 81. Well, if you're paying attention and you're following along, you should be thinking those are perfect square numbers. Why is that such a big deal? Because at some level we're going to get to here, the square root of n. Which would you rather have, a sample of size 49 or 50? Well, 50 sure sounds like it's a round number, but taking the square root of 50 isn't as conducive to the math as a sample of 49. So you're going to see, at least when I write questions or when I give you examples, you're going to see a lot of perfect square sample sizes. All right, anyway, here in the first part, and I'm going to do several parts to this problem, I'm asking you to describe the sampling distribution of the sample mean. And those three pieces that we just talked about, the mean, the standard deviation, and the shape, those are the three things that I want you to be able to tell me about the sampling distribution of X bar. The mean of the sampling distribution is the same thing as the population mean. It's 12.05 ounces in this case. Mu sub X bar is always equal to mu. Sigma sub X bar is always sigma over the square root of n. Well, sigma in this case, the population standard deviation, I told you was 0.025, so now we need to divide that by the square root of 100. Why is 100 the perfect sample size? Because not only is it a perfect square, but when we're dividing by 10, the math's pretty easy. I'm a big fan of easy math. So here's 1, the mean, here's 2, and the third piece is the shape. Now notice in this example, I didn't give you a shape. I said it has a distribution. I didn't say it was normal. I didn't say it was skewed right. I didn't say it was skewed left. I didn't tell if it was an exponential distribution. I didn't tell you what it was. And the point is, with the central limit theorem, it doesn't matter. Regardless, because we took a large sample, that's what CLT stands for, the central limit theorem. Because we took a large sample, the X bar distribution is going to be approximately normal regardless. And so we can solve things using the X bar version of the Z-score. And that's what I'm going to have you do here in Part B.